What specific problem does your research aim to solve regarding in-context learning, ICL, in language models? And why is it important to understand the internal dynamics of ICL?
Our research aims to solve the problem of understanding the internal dynamics of in-context learning, ICL, in language models, particularly how different prompting methods affect internal representations and their geometric properties. Despite ICL's success in enabling rapid task adaptation, the mechanisms behind it remain poorly understood, which is crucial for improving model performance and stability. By analyzing how prompting influences the separability and structure of category manifolds in the embedding space, we reveal distinct computational mechanisms that can inform better prompt design and task adaptation strategies. Understanding these dynamics is important because it highlights the interplay between representation quality and readout alignment, which directly impacts the model's ability to generalize beyond pre-trained associations. Ultimately, our findings suggest that optimizing readout alignment could enhance the effectiveness of language models in various tasks, making this research vital for advancing natural language processing capabilities.
Can you explain how your proposed method or algorithm works, illustrating it step by step? Please detail the specific experimental setup, the types of prompts used, and the analysis performed on the internal representations.
Our proposed method investigates how different prompting strategies affect the internal representations of language models during text classification tasks. We utilized a synthetic dataset generated by Claude 3.5 Sonnet, which included sentences labeled with 3 categorical dimensions: sentiment, topic, and intent, allowing for a comprehensive analysis of representational effects. The experimental setup involved 2 main types of prompts: instruction prompts, which provided abstract task descriptions, and demonstration prompts, which included a variable number of labeled examples. We analyzed the internal representations by constructing category manifolds from the embedding vectors of sentences sharing a class label, measuring properties such as manifold capacity, dimension, and correlation structure. This analysis revealed that demonstration prompts significantly reorganized intermediate representations, enhancing separability and capacity, while instruction prompts primarily influenced the last token embeddings without altering earlier layers, highlighting the distinct mechanisms at play in task adaptation.
Could you provide a simple yet illustrative example of how the internal representations change when using different prompting strategies, e.g., demonstration prompts versus instruction prompts? Walk through the main algorithm steps using this example.
In our study, we examined how internal representations in language models change based on different prompting strategies, specifically using demonstration prompts versus instruction prompts. For instance, when using a demonstration prompt for sentiment classification, the model receives several labeled examples, which reorganizes its intermediate representations at early to mid layers, enhancing the separability of sentiment manifolds by reducing their dimension and improving correlation structure. In contrast, an instruction prompt, which provides only a task description without examples, primarily influences the last token embedding, leading to increased manifold capacity but with less impact on intermediate layers. The algorithm steps can be summarized as follows. First, we input the task-specific prompt, either demonstration or instruction, into the model. Next, the model processes the input, generating sentence embeddings at various layers. We then analyze the resulting category manifolds by accumulating the embeddings of sentences sharing the same sentiment label. Finally, we compute manifold capacity and other geometric properties to assess how well separated the representations are, revealing that demonstration prompts significantly enhance the model's ability to classify by optimizing early layer representations, while instruction prompts mainly affect the final output stage. This illustrates the distinct internal dynamics driven by the choice of prompting strategy.
What are the theoretical or practical benefits of your method over existing alternatives in terms of representational clarity and task adaptation efficacy?
Our method offers significant theoretical and practical benefits over existing alternatives by enhancing representational clarity and task adaptation efficacy through a detailed analysis of internal representations under different prompting methods. Specifically, we demonstrate that demonstration prompts reshape intermediate representations more effectively than zero-shot instructions, optimizing them for classification tasks and improving manifold capacity, which quantifies the separability of category representations. This increased separability allows for better alignment between the model's representations and the output layer, addressing the common failure modes of few-shot in-context learning, such as sensitivity to example choice and poor generalization. Additionally, our findings suggest that soft prompts, while effective, primarily influence later layers, indicating a distinct mechanism that contrasts with the broader impact of demonstration examples. Overall, our approach highlights the importance of understanding and optimizing readout alignment, which can lead to more robust task adaptation and improved performance across various objectives.
How was your method validated or tested, particularly regarding the dataset and metrics used for evaluating the performance of different prompting strategies?
Our method was validated using a synthetic dataset generated by the Claude 3.5 Sonnet model, which was specifically tailored to our research needs, featuring diverse sentences labeled with 3 categorical dimensions: sentiment, topic, and intent. This multidimensional labeling allowed us to analyze the effects of various prompting methods in a multitasking context. We employed manifold capacity as a key metric to evaluate the separability of category representations in the embedding space, which quantifies how efficiently task-relevant features are encoded. Additionally, we replicated key single-task experiments using established open datasets as a control to ensure the robustness of our findings. The performance of different prompting strategies was assessed through accuracy metrics, revealing distinct impacts on internal representations and task performance across various configurations.
What limitations or drawbacks have you identified in your study, particularly regarding the use of synthetic datasets and the analysis of representational geometry?
In our study, we identified several limitations, particularly concerning the use of synthetic datasets generated by Claude 3.5 Sonnet. While this approach allowed for precise control over task parameters, it may not fully capture the complexity and variability inherent in real-world language structures. Additionally, the metrics employed to quantify representational geometry, such as manifold capacity and individual manifold geometry, simplify the intricate tasks that occur within language models by focusing solely on classification tasks with predefined target labels. This narrow focus suggests that future research should explore a broader range of natural datasets to enhance the generalizability of our findings. Furthermore, we recommend investigating how other tasks, especially those requiring multi-token outputs, might influence representational geometry, as well as developing more advanced measures that connect geometry to complex computations.